I'm going to do it at the end. It makes more sense out of order. I was happy with the grades. Yes. Yeah, so the one that's called Catalyst, I'm going to do it towards the end. No, we're going to do it together. We're going to end it. I never use the microphone, so if you can't hear me, just let me know. First of all, hello, first-hand frauders. Nice to meet you all. I'm going to put a disclaimer on this class and say this is going to be the biggest class you're going to see at Berry College. All right, so of those who currently go to Berry College, how many people have a class of like 18, 20 or less? Yeah, pretty much everybody. Right, so this is a unusually large class because people are so excited about chemistry. Obviously. Perhaps. So, my announcement for those of you in here, let's see. One, your next mastering is due Monday night, and it covers chapter 13. So the stuff we're going to do today, elementary steps, molecularity, things like that. Not everyone has taken the first exam, so I don't have it with you to pass that. However, your grades are online in the Mastering Gradebook. So up to you if you would like to see it today or you want to wait till Monday. In general, the class average is a 76. 25% of the class got a 95 or better. 50% of the class got 85 or better. The other half did not get 85 or better. So if you are in the bottom half, I'm going to recommend that you guys come see me. We can sort out what may have gone wrong on that. So, yeah, kind of a binomial distribution. Either, what was that? No, because 25% of you got 95 or better. So there's no real point to this curve. Curve. Yeah, no. And that's it. Unless there's any other questions. Are you feeling better? Because if you still had the flu, I was going to say Alright. So, what we're going to do is we're going to finish up chapter 13 today. Monday, bring your chapter 14 PowerPoint. And once there's anything else, we're going to go ahead and get started. Alright, so where we had left off with our last bunch of material was looking at, little k's, Arrhenius equations, figuring out how activation energy is related to reaction rates. Right, the higher the activation energy, the more energy you got to put in to get the reaction to go forward. So, we need to look at reaction mechanisms and how we go about figuring out or determining if a reaction is likely to go forward and then how fast it is to go forward. So let's say I have this reaction right here. I have AB add together with a C to make an A and a BC. I could come up with two different ways, probably more than two, but we'll say there's two different ways this reaction could occur. Right, the first of which would be, let's say, AB, this molecule AB, first breaks apart. Right, something happens and it causes it to break into half. Then, I need to make this BC compound, so the B then goes on to react with the C to make a BC. Right? That, you could think through it. That seems like an option of ways that could happen. What we need to do is we need to check to make sure we have the same reaction at the end that we originally wanted. Right, so what we're going to do is we're going to add these two reactions together and cancel out anything that appears as both a product and a reactant. Right, so I'm going to add these two reactions together, looking up and down. What is a molecule that occurs in both the first and the second reaction on opposite sides of the arrow? B, right? B occurs here and here. Alright, so let me write this down here. Alright, so we're going to call B an intermediate. So it's both a product and a reactant. It first shows up as a product, and then that product becomes a reactant and goes on to make the final thing that we want. So when I add these two reactions together, it won't appear. It'll look like this. Is that the reaction I wanted? Yes. So this seems like a possible way that this final reaction happens. Alright, that's an option. Alright, I could also imagine a second way that this could work. I could imagine that A and B combine with C to make an ABC conglomerate. Alright, they merge. Right, and then that ABC combo goes on to break apart into A and then the BC. In this scenario, what is the intermediate? Right, the ABC is now the intermediate. It's first a product, then a reactant. So it won't appear in my final reaction, so let's double check to make sure we get the right. Is that the same reaction I originally wanted? Alright, so now we're in the scenario where I have two different mechanisms. We need to go about figuring out what would be the better option, and how do we go about experimentally determining which of these two actually occur. Bless you. Alright, so we're going to have to get some terminology down so we can talk about these. We're going to talk about these two things, molecularity and elementary steps. I did not leave you enough space to write in here, so I'm going to put my molecularity definition over here. Alright, molecularity is defined as the number of molecules that participate in an, that's not spelled right, what am I missing? Okay. And an elementary step. It's a great definition, but the use of the definition we haven't figured out yet. So, what's an elementary step? It's just spelled funny, I have to see A and yeah. Alright, an elementary step. This is going to sound like a weird first statement, but describes an actual event. Describe something not theoretical. Describe something that actually happens. Each elementary step has a EA and a little k. Okay, what is EA? It's an activation energy, and then K describes a rate constant, right? So it has both an amount of energy it has to be input, and it goes at a certain rate. Okay? Alright, elementary steps must add back together to produce the balance equation desired. Right, so elementary steps must come back together to put back together what we had or what you wanted originally, or what you know happened. So, using those as definitions, let's look back at our examples. Alright, so what are each of these reactions then? Alright, they're each elementary steps. So these are both these are both elementary steps. 2 elementary steps. They describe an actual event. Each of these will then have I'm going to call it K1 and K2. They each have their own rate constant. Right? So there's a certain rate for this reaction and a certain rate for this one that are not necessarily the same. And both of these add back up together to make the net equation that we wanted. Alright, if we talk about molecularity, which is the number of molecules that participate in an elementary step, how many molecules are listed here as reactants? Not a trick question. That is 1 molecule, right? Making me nervous. Alright, 1. That is 1 molecule. I mean, we could do the number line, but I feel fairly confident that you guys have got this. This is 1. So that's going to be called a unimolecular, whatever, reaction. I know, so complicated, right? Uni meaning 1, molecule meaning molecule. So 1 molecule. Okay, what if I look at this second elementary step? How many reactants? 2. Yep, good, good. So if it's 2, any guesses on what I should call this? Bimolecular. That's a bimolecular reaction. Alright, questions on any of that so far? Feeling pretty good, counting and stuff? Okay, good. Let's get to the confusing stuff. Yay! I try to warm you up. Alright, so the question is, let's see if I can do my crazy thing over here. Alright, if you're looking at the PowerPoint, don't give away the ending. It says mechanisms and rate laws. So, alright. So, as was on your test in the multiple choice section, right? No simple relationship can be assumed between reaction coefficients and reactant orders. Right, so if I have this as my reaction, right, so if that's my reaction, on your test there was a question, is this reaction first order, second order, 1/2 order? Can't tell. Why can't you tell? I didn't give you any experimental data, right? So the rate law cannot be assumed from the balanced chemical equation, because you would have to, you need experimental data. Alright, because I want to have something in terms of rate equals this right, and so those exponents, I need some sort of experiment data in order to figure out what the exponents are. Unless you're looking at elementary steps, in which case they totally do equal the reaction orders. You guys look super excited about that. Okay, so for those of you who aren't normally in this class, I'm actually fairly hilarious. The classroom today is a little low energy. I'm assuming it's a Friday. It's the excitement of the test that they had on Wednesday. Usually my jokes kill in here, so I just need to bring my level up here, and I need to tell more funny jokes. All right. I was just checking, make sure the microphone was on, that you guys can hear me in the back, because maybe that was the issue. It's just like you couldn't hear me. Apparently not. That's not the issue. Okay. No. You can tell the first-hand Fridayers afterwards how desirable this class is to get into. It's a hot ticket. Hot ticket. Yeah. I tried to keep the fist fights down. So, like, no, you guys don't have to fight over me. It's very flattering, though. Alright, so the issue is elementary steps do equal reactant orders. So, let's take a look at, let's do this one. Let's say that's the reaction I'm interested in. And so my elementary steps would be, I'll number them. I'm going to leave off the gas, because this is all in the gas phase, we're assuming it's all still in the gas phase. Yeah, because I had 2 NO2s. I do right there. You're welcome. No. One. That should be. Yep, sorry, that should be a 1. I changed it to a 2. See, I was telling jokes, now I lost my train of thought. Alright, so now I have 1 step and 3. That's just an N by itself. There could be. We're just not doing one with coefficients. Right, so this is like my intro one, and then we'll do the more challenging one. So this intro one only has 1 as coefficient. Then we'll move up to not 1. Then we'll get crazy. I might do some fractions. Fractions! Yeah, okay. I like fractions. It's how you read a ruler, right? Fractions and stuff. Yes. It just happened to be this reaction. This particular reaction had an NO, and an N, and an O3. Yeah, you'd have to experimentally determine this. That's the other thing. Elementary steps are experimentally determined. No, no. There's no way for you to know the elementary steps without doing the experiment to determine them. That make sense? Like, I have to give you the elementary steps. Yeah. Alright, so then... That should be. Where have they been missing from? Yeah. Because then when we add them up, right, we add them up, this, that, and that's what you want. Yes, it's just nitrogen all by itself. Yeah. I changed my mind midstream. Alright, so let's say, right, these are our 2 elementary steps. And I want to know about this first elementary step. Right, so the rate law is based on the reactants, just as a reminder. And so our rate law for this elementary step, looking at this, what is the reactant? NO2, how many of them are there? 2, so what should be the coefficient? Yeah. So for the first elementary step, that is it. Okay? I can't do it for the second one yet, and we'll talk about it like in 5 minutes, why I can't do an easy rate law. But any guesses why I can't do an easy rate law for this? Right, these reactants don't actually exist, right? They're intermediate. And so I can't measure concentrations of things that exist for only fractions of a second. And so we'll have to find some ways around solving this issue in a minute. Let's do another one of these. Yes, let's do another practice one. Let's say I have every class I say I'm going to get rid of that green marker, and I never get rid of it. It's always so dried out. All right, let's say I have this. Alright, let's say I have hydrogen reacting with iodine chloride. Why not? Alright. To make some hydrochloric acid and some iodine gas. This is my net reaction. So if I look at my elementary steps, let's say the first elementary step is that the hydrogen gas reacts with one of the iodine chlorides to make a hydrogen iodide and hydrochloric acid. Let's say the second elementary step takes this, reacts with the other ICL, and an iodine. Okay, looking at this, first question would be, are there some intermediates? What is an intermediate? One of my favorite molecules, right? I feel like it's the friendliest of all the molecules. Unlike nitrogen monoxide. No. That's an unfriendly one. It's like right off the bat saying, don't talk to me. I don't want to participate in any of your stupid reactions. Which is fine, because it's toxic. I wouldn't want to work with it anyway. If a molecule had a personality, I like to imagine all molecules have personalities. They don't really. Alright, so let's say if I wanted to write the rate law for this, I'll help us out, right? So far, so good. That's funny for those who aren't normally here, because every single one of them starts off that way. So they all start rate equals K. So I'm actually not helping them at all. What should I put in my first bracket? H2, does it get an exponent? No. What about my second bracket? What does it get? ICL, does it have an exponent? I'm doing just the first one. I can't do it for overall. Yep, they're just ones, right? So I can't do it for the net equation because I don't have the experimental data. I can do it for the elementary step, right? So even though in the net it's a 2, the rate law for just this elementary step is a 1, Jordan. just whatever the coefficient is. It is simple, which is why we do the second. I make it complicated, then I make it uncomplicated, to make it more complicated here in a minute. Yeah, I just throw you on an emotional roller coaster in here. Easy. I get it. Oh crap, I don't get it. Oh, maybe I do. No, maybe I don't. Yeah. That way. Just one. Nope. It would have a different rate law. Yep. So, that's my next point. How do you know which one to look at? You're reading my mind. Yes, the question is, how do you know which of the elementary steps to look at? That's part of it, and part of it is, how many people have taken biology? What is the RDS? Oh, I hear some mumbling. The rate determining step. So, in biology, maybe in animal science, you talk about rate determining steps. That is how we decide which elementary step we look at. So the rate of the overall net equation is pretty much going to be solely determined by the rate of the slowest step, called the rate determining step. Right, that seems pretty straightforward. So, as you know, all my examples mostly revolve around food. So let's say, yeah, I know, it's almost lunchtime. Unless you're in First Time Friday, in which case you have like another hour. Sorry, guys. Yeah, sorry about that. So let's say, for example, we are going to that's not spelled right. Too many H's? Sand switches? You know, it's like the thing with bread, cheese in the middle, with some heat. Heat applied. I didn't do real well in spelling in like 4th, 5th, 6th grade. I mean, if I have a word I don't know, you just plug it into Google and it says, did you mean? Usually yes, copy paste. Right? I mean, you don't really have to know how to spell anything. Alright, so let's say we're going to make a grilled cheese sandwich. What is typically the very first thing you need to do in order to start making a grilled cheese sandwich? Obtain some bread, obtain some cheese, right? So we'll do that in either order. Alright, so now I have my bread and my cheese. What do I need to do next? I need to combine them in some way. I'm probably going to put the cheese in the middle. I mean, your option, I guess you could have cheese on the outside, bread in the middle. But I'm going to do the classic, bread on the outside, cheese in the middle. I knew I was going to get into trouble. Assemble your sandwich. Alright, so now I have my sandwich assembled. What do I need to do next? Yeah, well, that's a delicious step. I mean, you could certainly go butter-free, but why? Really? That seems silly. Okay, that's a delicious step. That actually has nothing to do with chemistry. This would be the delicious determining step. That's something else, not science. Alright, now we have my buttered sandwich. So now we need to grill it, right? In some sort of way. You have to either put it on a panini press, or you put it in your George Foreman, or you put it just on the stovetop, or you slide it. Yep, whatever you want. However you make yours. Alright, now you have your hot sandwich ready to go. What do you need to do next? Eat it. I was going to say eat sandwich, but I can't spell sandwich, so I was going to say eat it. Alright, that's the satisfying step. Of our 6 steps listed, which is the one that takes the longest? The grilling, right? Unless you're a really slow eater, which I am not. By the time we get to that, I am just feeding into my mouth. So this would be our rate determining step. That is the slowest step of all of them. This step right here determines your production rate, right? Determines how fast you can get to the product. So even though we have all of these elementary steps, right, this step would be bread out of bag onto plate. You know, cheese out of bag. Where do you put cheese? Cheese in bag? Slab? I don't know, do you have a slab of cheese? However you get, I don't really eat cheese. Fun fact about me, I don't eat cheese. It's disgusting. It's squishy and it smells funny. It gets caught in your teeth. I don't like any of that. So I live a cheese-free life. Ooh, yes. In a pinch, I will eat pizza. Yeah, it is not one of my go-to foods. Yeah. Pizza problem to me, an intervention, a pizza intervention. Yeah, yeah. Yeah, if I have to, if like all else fails and that's the only thing in our house, then I'll eat pizza, but I typically do not eat pizza. Alright, so all of these things, right, so now we're at the rate determining step. So, the question is, how does that relate to chemistry? At least, it should relate to chemistry in some sort of way. I'll see what I can do about that. Yeah, I don't have anything with me. But I could maybe come up with something by Monday. Alright, so let's instead look at a chemistry example. Alright, let's say I have these 2 elementary steps. Alright, so maybe thinking, how would you know if it's slow or fast? I would have to tell you, or provide some sort of experimental data so that you could determine which one was the faster or the slower reaction. So let's say I did the experiment and I found that this step number 1 was the slow step, and once that happens, this step is the much faster step. My questions are, first, what is the overall reaction for these 2 elementary steps? So how do I solve that issue? What do I need to do to these 2 things? I need to add them together in some sort, right? So what are the 2 reactants? Okay. What coefficient do I need in front of the SO2? Okay. Let's think about that. Yep. So what coefficient do I need in front of the SO2? Right. Right, so when I add it together, right, you cancel them out. You figure out what's left. Questions on what I just did? All right. All right, so then which reaction 1 or 2 will be the RDS? 1. Okay, good. So then, final question is, it will be, yes. As long as you know the elementary steps, then yes. That's kind of what I was getting at here. The rate of net reaction is the same as that of the slowest step. So, if 1 is the slowest step, what should I put in the bracket? And then what exponent should it have? 2. Because even though the net reaction only has 1 SO2, I put in 2 in this elementary step. So even though it cancels out, it's still part of the elementary step. It's an intermediate. It doesn't show up in the end, but it's still part of the elementary step. Look at, yes, if they are reactive. Right. We're going to look at some examples in our last 10 minutes of when that's not always the case. All right, so this is great, right? The slow step was the first step, slow them fast. If it's slow them fast, very straightforward. What if it is not slow them fast? What if it's a fast, slow, fast? Like dancing. Huh? No? Alright, so let's say I now have this. This is my net reaction. And we found the 3 elementary steps. We found the hydrogen gas breaks apart, and each of the hydrogens go on to do a reaction by themselves. 2 things we need to be concerned about. 1, we now have 3 steps, right? The first of which is fast. The second of which, when we go to write the rate law, we're going to see something funky. We're going to see if we can solve it. Alright, so first thing, we make this assumption that if we have a fast step before the slow step, right, slow step being our rate determining step, we're going to assume that that first fast step is at equilibrium. Alright, so I have this. How do you look at the equation and say you're at equilibrium? What tells you? What is different about the arrows? It's now both directions, right? It means that I could go forward or I could go backward. I have an equal likelihood of going either direction. A single arrow tells me distinct preference. It's definitely going to go in one direction. Double arrow means, you could go either way. It's happy doing both. Alright, so the double arrow indicates that the forward and reverse reactions have equal rates. So it's as likely to make single hydrogens as it is to make hydrogen gas. We make that assumption so that we can do some other things. Alright, so of my 3 steps, 1, 2, or 3, which one do I make the rate law from? 2, right? It's a slow one, so let's go ahead and write the rate law for step 2. What is going to be the issue with writing the rate law in this way? H is an intermediate, right? So I don't ever know the concentration of it. I know concentrations of things I put in. I can figure out concentrations of things coming out. But I don't have any way of figuring out the concentration of something that doesn't really exist. That's what we're going to do. So, step 1 states, right, that the concentration, how do I want to do this? Right, based on step 1, if I have 1 of these, I have 2 of those. Right, so if I have 1 of these, I have 2 of those. And if I'm equilibrium, the concentrations must be identical. Just as much making this as you had of that. So now I need to get in terms of H by itself, right, because over here I have H. So now I plug this in for that, but now I have a coefficient. The coefficient is now the exponent. We'll do another one. It would, no, that's not 1/2. I had 2 of those up here. And so I was just doing some algebraic rearranging. Right, 2 H's equals 1 H2, and 1 H equals 1/2 H2. Let's do another one. What, the what be? It's raised to the power 1/2. That's the order, it's a half order. Fractions. That is the overall. Because it's based on the slow step, and the slow step is the net. Let's do another one. Let's do another one. Let's try another one. Let's try this. Let's look at another one. Let's try. Let's pick 2 letters. Let's do. Alright, first thing, let's figure out the net reaction. What would be some things that would cancel out? Right, that guy would be gone. Is there anything else that appears as a product and a reactant? Alright, this guy. Alright, so my net reaction Alright, so now I want to figure out the rate equation for this overall net equation. Which elementary step do I need to use? Alright, the second one. So what would be in the first bracket? Okay, it would be CD, and D is in the second one. And right now we have the issue again, right? CD is an intermediate, and I don't actually know its concentration, ever. What is something we know about molecule CD? Yep. Alright, we know that must be true. If this is at equilibrium, the concentration of this is equal to that plus that. So now we have something we can plug in. It would be easier if I did it this way. The things in the red parentheses are just substituting for each other. So what's the last thing I can do to simplify this? Chaos. It's chaos, so you can't solve it. Yeah, just put down chaos and say, Dr. Sorobic had a terrible question. Because you legitimately do not have enough knowledge yet to solve it if it is not in equilibrium. You can write chaos? Maybe. Maybe it'll be in the multiple choice section, which is the following best describes this. Anarchy, chaos, totally solvable. Because it was a reactant then product, not a product then reactant. No, that one went in as a reactant, came out as a product. I'll show you in a second. Officially, we're out of time, so I'm going to finish the last thing for this on Monday, and then bring your Chapter 14 PowerPoint. Hopefully it was scintillating. Yeah, let me just turn off my video.
So, where do you go from